All right, I'm Dan Wallach,
Hi, I'm Zoran Vladimirovich.
and this is week 2 of Comp215. Obviously, this lecture should have happened in class, but because of the flood, we're doing it on YouTube. And we hope that you take the time to watch the lecture before you dive into tomorrow's labs, but this will have everything you need. So we should probably mention both of us were lucky. Neither one of our houses took on any flood water. We both had electricity the whole time, and that makes us some of the lucky ones. But, it's been a very exciting week.
Yeah.
All right, on to the lecture.
Yes.
Let's do it. So now we will press this button and have recursive video. Okay, play. So, last week we learned about Java classes, Java objects, and we had lists full of objects. This week we're going to learn about lists of specific kinds of objects, and these are called generics. So, of course, before we get on with the class, let's talk about the hurricane. If you are impacted, if you have issues, if your computer was damaged, if there's something going on where the deadlines are going to matter to you, then please let us know and we will do our best to help you. All right, so when you visit Piazza this week, there will be a new PDF for the project and a new PDF for the lab, and inside of that will be another GitHub Classroom link that you will click, and then you will have a clone of all of our code. The code that we're going to be using this week is this edu rice week 2 lists glist. So this is a generic list. We're going to be walking you through it with some live coding at the end of this lecture. So the project will be adding several functions to glist, and the lab will be writing several lambdas that filter lists. So that's what we're going to be doing this week. Please make sure that the university thinks you are enrolled in the class. If you're not enrolled in the class, then you're not in Piazza and you're not going to be able to get any of the lab or project materials. All right. So, last week we built functional lists. We had an object list where you could add an object and get another object list. You could ask if a list contained an object and get back true or false, etc. This design is a great way to begin, but it has some problems. When all the world's an object, when you know that something is not just an object, but it might be a specific kind of object, you have to do these typecasts. So even though I know this is a list of strings that has hello, rice, owls in it, I still have to cast the resulting thing from saying, give me the head of the list. I have to cast it from an object to a string. These typecasts are ugly. We don't like ugly because we know it's lists of strings, so how can we make it do the work for us? We want to be able to say this isn't just a list of object, it's a list of string. So here's how Java lets you do that. So here we're defining a generic list, and we say this is a glist of t, or a list of t. T could be string, t could be integer, t could be anything. And you can see the static method here. The static method has its own type parameter t. So this makes an empty list of t, and we get back glist of t. So this is called a type parameter. So when we say glist.makeEmpty, the type parameter goes here to the left of the function, but to the right of the dot. It's a little bit ugly, but this is how we say make me an empty string of glist, and then we can add hello, add rice, add owls, etc. And notice down here, when I say list.head, I don't have to do a typecast.
So just one point. The generic type parameters are useful for convenience. As you can see here, you don't have to typecast when you take an element out of the list because Java knows that it's a string. but they're also useful for safety. If you make a list that you want to put strings in it, and you make it a list of object, you can put anything in there. So your list of string can get polluted with other stuff, and then when you cast it, you get a runtime exception. This way, the compiler makes sure you're not sticking integers or any other things into a list of strings. So a list of string is always a list of strings.
Right. So in this way, if you intend it to be a list of string, and then you accidentally tried to put something else, that would be a compiler error, and we like errors that happen early. Now, having to type this bit over here, having to type glist dot something make empty, somehow that feels a little bit ugly, and we're going to talk in the next several slides about when we can get away without needing to do that. So, when we say that this is a shirt of tea, we'll often shorten that to calling it a t-shirt. So, yeah, but that's the vocabulary. So, when you see that, this is a t-shirt, or you might say a t-list. All right, so there's a bunch of vocabulary that goes along with this style of programming. We tend to call them generics, but you will also sometimes see the complicated phrase parametric polymorphism. Those mean exactly the same thing. So we're saying list of T, or a generic list, or a list with parametric polymorphism. Those are all synonyms. I like generics. We've already had parameters to functions or parameters to methods. Now we have these weird type parameters. So these are type arguments that it feels like you're passing a type argument rather than passing an object argument. Those are the things inside the brackets. So generally speaking, when we say that code is polymorphic, that means you write it once and the same code can operate regardless of the concrete type. So this is all about our Zen coding rule number 1, don't repeat yourself. If we can write code that works for lists of strings and lists of integers and lists of anything else, and if we can write the code once and have it be correct for all these different types, that's a good thing. That's how we avoid repeating ourselves. Generics help make that happen. So, last week when we did our object list, we created this empty list singleton. So we had our class empty list, which implemented the object interface. So the class empty implements object list. So our class implements the interface, and we had a singleton. So this was a private static final, and this was the only place in the entire codebase where you'd ever say new empty. Everywhere else, you would just reference that singleton. So let's talk about how to solve this problem in a world of generic programming. So there's a little bit more going on here. So you'll see that first off down here, we have type inference. We don't need to say what the type is on this side. We're just saying, hey Java, try to figure it out from context. This less than greater than thing is sometimes called a diamond. And over here, we're using another weird thing called a wildcard. We're saying, this is a list of, it's a list of something. I don't know what. And this code is completely legal. The other thing is you'll notice up here we're actually doing typecasting. We're saying, take this singleton, which is of type glist of duh, and we're casting it from that to glist of t. And Java normally will scream at you and say, I don't know if that's okay. And we're saying, hey Java, don't yell at us, we know what we're doing. This is not something you ordinarily do, but it's okay to do here. Why? Because of the way Java really handles these type parameters under the hood. There's only ever one real class. Whether it's a glist of string, a glist of integer, glist of foo, at runtime, there's just glist. All those type parameters disappear at runtime through a process called type erasure. So what that means, if you look down at the bottom here, when we write code that says this, glist of something, singleton equals give me a new empty. The actual code that the compiler emits looks more like this. It says make a list of nothing. And so that's why we know we can get away with this, because all the type parameters only exist at compile time. They disappear at runtime. And that has an interesting side effect. You can never say this. You can never say give me a new t. because at runtime, those t's are all gone. So you're not allowed to do this, and in the coming weeks we'll talk about how we work around that in Java, and we'll mention that some other programming languages that are similar to Java, like Microsoft C#, have a nifty trick called reified generics, which means that you actually can say, give me a new t. But Java doesn't have that, and we'll work around it later. But that's why we can get away with having one singleton, because we know that there only is really one class, and there's only really one singleton, because of this interesting type erasure property. So the trick to getting away with it, though, is we need to make sure that we never accidentally try to return something from that empty list, because we don't really know what t is going to be. But that's okay, because what's the head of an empty list? That's an error. There is no head of an empty list. So if you tried to ask for its head, it just explodes at runtime and says, no such element, can't do that. But when we're calling add something to an empty list, this code at the bottom of your screen, we're now calling give me a new cons, and that's fine, because cons will deal with the type. The empty list doesn't care. More on this in a minute. So it's really nice when we don't have to do type parameters. It's nice when Java can figure it out for us, and Java is pretty sophisticated at this. So in this code up here, when we are saying make me a new cons, I don't need to say new cons of t. Java can figure out from context that I'm trying to return a cons, so the cons that I'm making here is getting returned there, and so the type parameter had better be the same. Generally speaking, if you're not sure, try leaving out the type parameter and just using a diamond. If it works, you win. And sometimes you don't even need the diamond at all. And again, if it works, you win. So you just try it. The only times when you're going to have a type parameter declared are when you're declaring a variable, when you're declaring a return type, and when you're declaring arguments to a function or method. In almost every other place, Java will try to figure it out for you. And you can, when in doubt, put in the type parameter and see if everything works when you delete it. So, the stuff up here in green will work. Here we are making a list of integers, and I can say, give me give me an empty list of integers, and then add 1, and then add 2, and then add 3. That works fine. Likewise, I can say, give me an empty list of integers. Notice the absence of a type parameter here. In this case, but not this case, Java can figure it out. Kind of annoying, but that's how it is. And then once we have an empty list of a particular type, we can add 1, add 2, add 3, and that works. Whereas the two examples down here in red don't work. Java cannot infer the type parameter in this position. And if you try to leave it out altogether, in these two red cases, the Java compiler simply will say, I don't know what to do here, and will fail.
Right, because in the first case, Java knows that you're calling glist make empty, and then you're declaring the type of your empty list as the glist of integers, so it can infer the type t over here. In the second case, you're calling these add methods on it, and the compiler can't figure out where is this actually going to be executed and what's the type going to be of the whole thing in the end. So it doesn't know how to call make empty with a specific type. So you either make your empty list like this if you hate passing types, or you make your make empty list with the type, and then everything works fine.
So, we're going to talk a lot more on Wednesday about how these generics work. But for the rest of today's lecture, we want to talk about lambdas. So, back in the bad old days, back before you took Comp215, you might have written code like this. Let's say I have a list of integers and I just want the even integers within my list. So I would start with an empty result list, and then I would do some kind of loop. Give me every integer in the original list, and if that integer mod 2 equals 0, therefore it's even, then I would add that resulting even number to my result list. This kind of code is ugly, it's error prone, and that's not how we write code in Comp215. No. Because no mutation. That's our rule. We don't want to be mutating I, mutating result list. All of that mutation is an opportunity for you to have bugs. So we're not going to do this. No mutation. Instead, we're going to write code that looks like this. So here's a function evens. You give it a list of integers, and it gives you back a list of integers. And what it says is take my input and filter all the integers, I arrow, I mod 2 equals 0. That expression there in green, that's a lambda expression. So that's a function that takes an argument and returns takes an integer in, a boolean out. And filter is just another operation on a glist. Just like we can add to a list and get another list, well, we can filter a list and get another list. This is how we're going to be doing stuff all semester long. So what exactly is this lambda? Well, it's a function without a name. So in this case, I arrow I mod 2 equals 0. This is a lambda that returns a boolean. And notice what's not here. No type declarations. We never say that I is an integer. We never say that the lambda returns a boolean. Java figures it all out from context. From the fact that you were using this lambda as an argument to list.filter, therefore it must be having as an input the same type as the list, and it must be having as an output a boolean, because that's what filter requires. Java figures it out. So this means that your code is cleaner, shorter, easier to read, and that's a good thing. So how does filter work? Here it is. So filter takes as an argument a predicate, which is just a function that returns true or false. And if the predicate tests true on the head of the list, then, okay, so predicate is a lambda returning a boolean. More on that in a second. We're going to apply that lambda. So predicate.test, and if you're not sure what predicate.whatever, IntelliJ will auto-complete it for you. So we're going to test that lambda on the head of the list, and if it's true, then we will have this case where we say recursively filter on the tail of the list and then add the head value on to whatever comes back from that recursion. But if the predicate failed, that means that we don't want that element, so we're just going to return recursively whatever filtering on the tail does. We'll deal with the base case of empty lists in just a minute. But you can see that this is recursive code that follows the structure of a list. A list is either a head value and another list, or a list is empty. Here we're just showing you the case for a head value plus another list. Okay. So, predicate is a function that returns Boolean. Operator is a function that returns the same type as its input. So you'll hear about unary operators. So that's like a trigonometric function like sine, cosine, tangent. They take some type in and they have the same type out. Binary operators take two of something in and one of the same thing out. So addition, subtraction, multiplication, those are binary operators. Don't confuse binary for bits with ones and zeros. Binary means there are two arguments when we're talking about a binary operator. So a function is a more general purpose thing. A function, the arguments and the results could be a different type. Similarly, we will bump into suppliers, which produce data. So we might have something where every time you call a function, you get the next line out of a file. That would be a supplier or a producer. Conversely, a consumer eats data, does something, and returns nothing. So when you call system.out.println, that is a consumer. So these vocabulary terms, predicate, operator, function, supplier, consumer, are just different kinds of functions different kinds of lambdas that we will be using over the course of the semester. You might be coming back to this slide whenever we talk about a predicate or an operator. Java turns out to support many different ways of writing exactly the same lambdas. So 1+, you can see I have version 1, version 2, and version 3 here. These are all exactly the same function. X to x plus 1, or you can put parentheses around the arguments if you want. You can have an open curly brace and have any block of code. When you do a curly brace, you have to have the return keyword, but you can get rid of the return keyword if you don't need it and get rid of the curly braces. So the first form here is the most concise. It's preferable. If you can use it, great. If you need to do something more complicated, then you use the second form. You can explicitly declare type parameters if you want. So if you really want to say it's an integer, you can. You really don't need to, but you can. And here's another one. This is just a static method. This is a function that takes an integer x and returns x plus 1, and I have this interesting syntax where I can say the class foo, here it is, class foo, : 1 plus x. So I'm naming that static function. Turns out you can also do instance methods this way, but not, let's keep it simple for now. I can name a function I write this way, or I can have one over here. Each of these versions, version 1, version 2, version 3, version 4, all of them work exactly the same way. Although I want to point out that we're using capital I integer rather than little I int. Why? Because Java type parameters must be boxed types. They must be object or other object types. They can't be primitive types like int or lowercase d double or lowercase b bool. You have to use the uppercase boxed versions. But Java will go out of its way to convert back and forth from the primitive types to the box types and back. So even though this function takes an integer with a capital I and returns an integer with a capital I, this is using the little I int, and you don't have to go back and forth. So Java is hiding it from you. But at least be aware that you can only have boxed types or object types as type parameters. So, over the course of the semester, you will be seeing many different functions that we define on lists. More on Wednesday. But to give you a sense, we might say list.map. So what this is doing is give me a new list, which is the old list with this function applied to every argument. So we could say, give me a list of all of those integers, but I want them all squared. List.filter, which we showed you earlier, will filter a list. It'll give you only the elements where the predicate is true, and of course ignoring the elements where the predicate is false. We might have a sort method that takes some kind of comparator function that will tell us which one is greater and which one is lesser, and with that we could then sort the list. You're going to be implementing something like this next week, but not right now. So here is how mapping might work. I have some original list of integers, and then the squares could be originals.map, and what's a function that takes an integer and squares it? I arrow I times I. Similarly, I might want to take a list of strings and convert them from all caps to lowercase, or from some bouncy caps to lowercase. So in this case, when I say strings.map, x arrow x dot to lowercase, we know that x is a string because we're operating on a list of strings, and every string has a to lowercase method. That's built into string. So in this case, we're converting from strings of whatever case to only lowercase strings. You could also pronounce this as string : to lowercase. In this case, I'm converting from strings to integers. I want a list of the lengths of those strings. So in this case, it's string in, string out. In this case, it's string in, integer out. And if you tried to put this and you wrote string over here by mistake, Java would say that's a compile error because I know that that function returns integers, and if that says string, it doesn't match, and Java will say no and give you a compile error, and we like that. So, your lab this week, you will be writing three different lambdas that filter lists. So, even though you have the code right now, please don't start working on it until you arrive in your lab, and we will have lots of TAs and labbies around to help you if you get stuck. Now, we're going to do some live coding. We're going to show you how to implement reversing a list, and our live coding will also show you a recursion style where you pass along your work in progress. And we're going to demonstrate glist.map. All right, here we go. So here is IntelliJ, and here is the code that you're going to have this week. If you want to learn more about, hey, where does this car and cutter and con stuff come from? Here's a great thing. Go read it. There's a lot of good stuff in this engineering note. Go ahead and read it, but that's not what we're going to do in lecture today. So here's what we showed you earlier. So we're in the middle of our glist interface, and our glist has a bunch of, so a static method to make an empty, and we have, every list has a head, every list has a tail, and we have a default method to add something to a list, so it doesn't matter whether it's an empty list or a cons, we get the right thing. Length, empty, contains, filter, map, etc. These folds we'll talk about more on Wednesday. Don't panic, don't worry about that yet. And you'll notice, range int, this is what you're going to be doing for your project this week, so don't worry about that either. Several things you'll be doing for your project. So what I want to do is define an interface for reversing a list. So it's not going to be static. This is an instance method. You need a list before you can reverse it. So
or you need to pass a list that you want to reverse to a static method.
Right.
In this case, we want to reverse the list itself.
So the return type will be a glist of t, because we have a glist of t and we want to reverse it. And we don't need any arguments. So that's it. We've now defined the interface. Now, every list will now have a reverse method. And because we're good programmers, we're going to write some Java talk. We're going to say returns a copy of the list in reverse order. Now we've written good Java doc. That's important. If we go down here, now we're going to have to deal with two cases. We're going to have to deal with our cons case and our empty list case. And IntelliJ is unhappy. It says, hey, wait a minute, you need to implement a reverse method. Yep. So we can be very careful with the red light bulbs. They can do lots of damage, but this one is all right. We don't want to implement add because we get that from above. We want to implement reverse. That's fine. There it is. Right now it says return null. That's bad, but we'll leave it for now. We'll come back and put it in later. And of course we have to do the same thing for empty list. We want to implement the method. Reverse is good. There we go. Now before I implement this, I need to write a test because I like writing tests. So what would be a good test for reversing a list? Well, for starters, let's see. I'm going to cut and paste some code here. It would be helpful to have an empty list. It would be helpful to have a list that looks like that. And hey Zoran, what would happen if I reversed an empty list?
I'm guessing it should be an empty list.
How about that? So we can write a test for it. So what are we expecting? So right now, I'm not sure I trust my equals method to compare two lists to each other, so I'm going to convert them to strings. I'm expecting to get no string out when I do the original empty list dot to string, because I'm making an assertion that I had better damn well be true, and I'm expecting that if I do empty list dot reverse dot to string, it will continue to give me nothing out. That seems like a pretty reasonable and simple test. So what about my hello rice if I convert that to a string? I'm expecting, so our toString method puts white space between them. So is this going to be hello rice owls or owls rice hello?
Owls rice hello, because you're adding the owls last.
All right.
And then you're going to be printing them first.
So even though I'm pretty sure I know what the answer is, I'm going to make a test for it anyway. And now I'm going to make it backwards order. So now I've got a pretty good set of tests. Are they comprehensive? No, far from it. But if these tests pass, I have some confidence that my reverse method is going to work. Hey, let's go run them. We're going to run the tests. And Java says null pointer exception. Yep. So test reverse here failed at line 46 because empty list.reverse returned null, and null is not allowed. And last week in lecture we told you we don't use null in this class. We're better than that. All right, let's start with the simple case. What should we do when we reverse an empty list?
Just return an empty list.
All right, well, we need one of those. Where are we going to find one? Well, we have this singleton right up here, but it's of this goofy glist of I don't know what type. So we need a way of getting an empty list of the correct type. Now it turns out we have one of those. It's right there. So we're going to return, we're just going to call make empty. Something broke. I don't know what happened.
Might have deleted a...
Something bad happened. Ah! Something weird happened up here, and I'm not really sure why, but we're gonna fix that.
You hit a paste accidentally.
Ah. Editing errors. So, note to use the student. When things go weird and a bunch of red happens, sometimes you just want to hit undo, sometimes you want to look around and see what happened. In this case, somehow I hit paste up here on the top. Yes, even your professors have typos when they operate. All right, where were we? We were down here working on the empty list case first. So we're class empty, here we are, and rather than returning null, and rather than returning this singleton, which we would have to cast, instead, we're going to return make empty. That's it. So we're going to call the empty function, and now we don't have to monkey around with typecasting or anything else. Nice and simple.
Because make empty does that monkeying around for you.
Yep. All right, let's rerun our tests, shall we? And what we see is, now we got a little bit further. We passed this test, we passed this test, we passed this one, and we failed that one. And once again, we got a null pointer exception. Boo, we don't like nulls. So let's go find that code and fix it. On the top? Ah, there it is. So here's the thing we need to fix. We don't want to return null. So here's the trick we're about to learn. Remember, a list is two things, a head value and a tail list. So the trick is we want the head to end up at the back. That's an interesting problem. So when we did something like filter, we could do this clever thing where here's the recursive part. Recursively filter on the tail, and then when that's all done, add the head value back onto it. We can't do that trick when we're reversing a list, because we can't recursively do something with the tail and then bolt the head on, because the head needs to go at the end, not at the front. Oh boy. So we need to do something slightly more clever. And what we're going to do is we're going to implement a helper method. So here's how that's going to work. Well, how should we do it, Zoran?
So we need a way to remember what the state was, so that when we recursively pass the rest of the list, we know what is it that we need to add on top of the list when we come back. So we have to pass the sort of intermediate result as we are traversing the list. We have to remember the intermediate result so that once we get to the end of the list, we know what's the proper thing to do.
So what I've done here is I have created a reverse helper function. And what we're going to do is we're going to pass along to this reverse helper this intermediate result, which we are going to be, every time we step, we're going to add the next thing to the front, and by the time we get to the end, we will have added the last thing to the front of this. And then once we run out of other materials, then we'll be done. So it's going to look kind of like this. So first off, when we're reversing, what we're going to do is we're going to return reverse helper, and what are we going to start with?
Empty list.
The empty list. How do we get the empty list? Make empty. So initially, the intermediate result will be an empty list. And what we're going to be doing, if we're in this side, in this case, we know that we are adding something to the, we can take the current head value and we can add it to the front of intermediate result, and then we're going to have a recursive call to reverse helper. So it's going to look kind of like this. Return a call to reverse helper where, oh, but not normal reverse helper, tail val. So we're going to call reverse helper on the tail, and we're going to pass along the intermediate result where we add the head val. Except wait a minute, that doesn't work, because reverse helper isn't always defined. It's only defined here in cons. It's not defined in the empty list. So let's do this a little bit differently. We're going to make it a static method, which means it needs to have a type parameter because it no longer gets the type from up top. And it's going to have two arguments, glist t input and glist t output. And every time we march along, we're going to peel something off the input and stick it onto the output. So now it's going to look a little bit differently. It's going to look like this. Okay, so the output is initially, hey, wait a minute. We're going to initially pass it this as the input and nothing as the output. So far, so good. Well, we need to take the head value off the input and attach it to the output. So it'll look like this. We're going to have a recursive call. So input.tail, where we're tearing something off the input, and so we could actually be a little bit, we could say tail, which just, this tail is just that tail, or we could, say tail val either way. Actually, wait, no. So you see, it's a little bit unhappy. Why is it unhappy? Because, hey, what if that's an empty list? Hey, what if that's... So Java is actually warning us that there might not be a tail val, because there are two cases here. This input might be a cons, or this input might be an empty. So we actually have to deal with both cases in here. If input.empty, then something else something. So in this case, what do we do if the input is empty?
Just return the output.
Easy. In this case, we know that the input is non-empty. So we know that calling input.tail won't explode. And now where the input shrinks by 1 each time, and the output grows by 1 each time. And we know that once we hit an empty list, once the input is empty, we'll return the output. This particular style of coding, where a function returns a recursive call to itself, has a special name. This is called tail recursion. Now, many other programming languages, when they see this, will quietly convert it to a loop. So the recursion actually magically disappears, and we're not doing function calls anymore. Java, unfortunately, is not that smart. So later this week and into next week, we'll learn how to deal with this in Java. For now, this code is correct, but if the list gets too big, this will explode. So that's a little bit unfortunate. But for today's lecture, we'll deal with it and we'll fix the problem later. But for now, let's run our tests. Run glist test. And what happens is it passed. All of the tests passed. So, are we done? Is it debugged? Maybe? Maybe not?
It satisfies that simple test. We probably want to write more tests at this point.
So at this point, I think we've demonstrated to you the process of writing first the interface, then getting some stubs in place just to the point where your code will compile, then writing some tests, then verifying that your tests fail, and then making sure that your tests pass one by one until your tests are happy. This is the general purpose way that you should do coding in this class. And not just in this class, this is a general purpose way for the rest of your life of how you should write code. Build the shell of an interface, write a bunch of tests, and then write code that you think is going to work. And then when your tests are happy, now it's time to decide whether you need more vicious tests or whether you think you're done. For today's purposes, we're doing pretty good here. And that means let's go on and talk a little bit about map. Okay, we're not going to spend much time on this, but I want to mention that we have this map function. So we're mapping a function. Okay, let's break this down slowly. We're inside a list of t, which is way up here. We're inside a list of t. So t is some type, we don't know what it is, and we're mapping from t to some r. What's r? It's a different type parameter. So the map method on a list of t takes a second type parameter r and returns a list of r. Woof, that's a little bit complicated. So let's say that again one more time slow. We are currently defining a method on glist of t. So we want to apply a function from t to r. We don't know what r is, so r has to be another type parameter. We put that out here to the left, and we're going to be returning a list of r, and this function is a function from t to r.
So for example, if you have a list of strings and you want to create a list of integers for a length of each one of those strings, then your function will be a map from a string to an integer, and the result of this map is going to be a list of integer. That's a concrete example. Now we want to write code for a map that works, that will do this for any list of any things. So if you have a list of cars and you want to get a list of colors of those cars, this will still work. If you have a list of strings and you want to get a list of integers for the lengths of strings, this will also work. So you want to write a generic map implementation that maps any lists to anything else. For that, you need to provide a function. So for each element, you need a function that maps from T, which is the type of this list, the type of an element of this list, into an R, which will be the type of the result.
Okay, so let's show you how that works. We're going to go straight to the tests and show you some unit tests for this. Then we'll show you the implementation. So, I don't have any tests for map. Let's make some! Okay. All right, so we might have a, when in doubt, we're going to start with some of these things to help. And let's say we want to get the lengths of those strings. So I might say glist integer lengths. And we're going to start with that hello rice, and we're going to map. So what's the input to the function? It's just, it has some string s. Note, we don't have to say what the type is, and we can say s dot length. That's IntelliJ's autocomplete being happy. And now, okay, IntelliJ is actually giving us a little warning here, and it's saying that you can simplify this. And so you can click on it, and the little yellow light bulb says replace lambda with method reference. Always think 3 times before you do this, but this time I know it's okay. And it's going to say, we're really mapping the string length function onto that list. So undo that and that. Those are exactly the same. They do exactly the same thing in the same way. So let's write some tests, shall we? So we're going to convert that list to a string. Okay, the first thing in the list is owls, then rice, then hello. So this should be 4, 4, and 5. Those are the lengths of those strings. And it should be lengths dot toString. Simple enough. Let's verify that that works.
You can run just that test.
Yeah, it's true. We can just hit this nice little play button and run it, and it passed. So you can see that even though there are some pretty complicated things with, the map being defined with an extra type parameter and all that, the code that uses it is actually really straightforward. I don't need, I could, I guess, put in here that the type parameter is an integer, and that works. But notice how IntelliJ makes that gray. It says, yes, I know, but you really don't need that. I can figure that out for you. So, in fact, it'll give us a little yellow light bulb, and we can remove that. And again, hey, I'm not confident. I can run the test again, and the test continues to pass. So, before we go, I just want to briefly show you the implementation of map. So let's go full screen again. So there are again 2 cases. We have to deal with empty lists, and we have to deal with head and the tail list. So let's go find the implementation of this. Well, here's the empty list case. This is really straightforward. What happens when you map a function onto a list with nothing in it? You get a list with nothing in it. So the base case is really simple. Easy. Piece of cake. Here's the non-empty case. In this case, here's the recursive call on the tail. So we're going to map the function on the tail recursively, And then when that comes back, we're going to apply the function to the head and put that back on the front of the list. So it's a little one-liner, but there's actually a recursive call and a bunch of neat stuff going on in here. And you don't have to write it this week. More next week. And you might be saying, hey, what's that fold thing? More on Wednesday. All right, anything else we should tell them today, Zoran?
No. Hope you guys are still dry and recovered, and we'll see you in class on Wednesday. This week's project is more complicated than the first week, but we're still not up to the full-blown don't panic mode. Although, again, start early, write a bunch of tests of what your code should do, and then implement that stuff.
Right. We certainly recommend that you start your projects first. Start your project, well, first, do your lab on Tuesday or Wednesday, then jump into the project. The lab has you writing some lambdas and will be there to help you. The project has you writing a number of functions inside glist, and get started, Wednesday. Get started Thursday. Wednesday's lecture will be helpful for you to do the projects. But this video that you just finished watching has everything that you need to do the labs and to warm you up for the project.
All right. Good luck.
All right. Good luck.